We are going to talk about one of the products that we've been working on just for a couple of months. So it's titled Invoice to VEC. There's a few things we'll talk about what that means. But our path, so our path is H2O, helping a client create AI to read documents to extract document information. So we'll be talking about that. Our team, there's four of us. So Brandon and I have been working with a particular client, well, PwC, who spoke earlier today, for about 2 years. I've been working with them for about 3 years, Brandon for 2. And for this project, we've stepped it up a little bit. So we've doubled our team. We have a couple other data scientists helping us out for this one. And then for all the products we build, of course, it's really not just the data science team. We have software engineers helping us out build the front ends that you saw actually on the screens. Our stuff was behind them earlier in the day. And the customer team, too. So there's a lot of people. In fact, one of them is practically on our team as well. So it's a fairly big group for this one, I suppose, especially in H2O terms, for making this product. We've been working on it for about 3 months almost now for this one. So we'll show you kind of where we're at. We are not done. We'll show you where we're headed, what the ideas are, what we struggled with, that kind of stuff. So quickly to look at the problem, and then we'll look at it a little deeper later. But we are extracting specific information from business documents. That's what we're doing. Various business documents. The information we're pulling out of them changes in the different types of documents. But that's the general idea. So we have an example of one here. You can see an invoice on the left. And in this one, we've kind of circled a few of the things we're looking at. Again, even for a specific document, we can look at it multiple different ways. We might talk about that a little bit. But in the right is where we're really headed. We're just standard old CSV. We're looking at actually the formatted information that we need to pull out of it. So it's a somewhat standard task, one you're probably familiar with. Other people are doing it. So what we'll talk about here, took a little deeper at the problem and the challenges in it, those that we've run into, and some that are just native to this problem from when we started. We'll jump right into kind of the high-end ones. So there's a lot of algorithms going on here. We're using many different things to do many of the different tasks. But the deep learning are the most exciting. So Brandon's going to talk about some of the image recognition, the bounding box identification type algorithms that we've been using for this task. And time permitting, we should be able to do a little bit about what we've learned, how we've prepared the data for this task. It's not a standard one when you're teaching these image recognitions. It's not cat, dog, mouse either. So it's a little different. So we'll walk through what we've done for that, what we've, where we succeeded, where we failed already in these 3 months. And then last, we'll try to finish up with how this connects into Driverless. So the product you've been hearing about kind of all day. We are using it for this product, and we'll talk about that. And then also, the real goal here is that the results of our work can be fed back into the product, that we can actually have some recipes out of this. So we'll take a look at where we're headed there. That would be quite a while away, but that's where we're headed. So the problem challenge again, pulling information out of these documents. When I tell this to a lot of people, they go back to, isn't this a solved problem? Why aren't you using OCR? Why aren't you using XYZ library? Why aren't you just using YOLO? Why is this a thing you're working on? And it's true. There's, many off-the-shelf solutions do a really good job at doing some of this task. And so, for example, we have, on the top, we have a document on the left, a PDF that we would typically see. It's not an invoice, but and on the right, a free tool on the internet, the first Google search, will give you something that looks really clean, really nice. Like not just OCR where you're getting the text back. It's preserved all the structure. It's put a lot of high-end features in there. It looks quite a lot like that document on the left, and that's for free. So the state of the art for pulling some of this information is pretty good. There are a lot of off-the-shelf tools. But if you take a closer look, and on the bottom, we zoom into what for us is not just a mistake, but it's a critical mistake. This has used an English language OCR, and so in the balance column, a lot of our data is tabular. That's a little different than typical OCR, typical NLP. We were looking at orientation. That's important to our problem as well. So here in the column of balance, we see it's supposed to be euros, but EUR isn't a word, and neither is USD, to be honest. But it decided that the probability of that it meant ADA was enough that it just switched it. So it used ADA, even though it probably read the EUR very well. And that's part of what you get with some of the OCR tools. They have deep learning underneath them. They're language specific. You can pick which one you want. It's not that we chose the wrong language. This is in English, but the tool has some pros and cons, and for us that'd be a critical con. So we can't just OCR it, although the OCR is really good on everything else just about in this document. But and it's not just one tool either. Even if we could, we could run this a couple different ways and resolve this problem, and we will actually. But there's other things too, and there's a lot of judgment that goes on. I'll skip to the third bullet point. In some cases, we're interested in the way that this document would be accounted for. Like Gary spoke about, how in 1400s we have double entry accounting. So we want to see how this document would be accounted. And so dates are really interesting to us, but not every date. Not every date on the page. We might have 7, we might have 100 dates. And only one of the ones is the correct date. So OCR will give us all those dates. It'll give us the text. We can read it, but that's not the entire challenge. We have to then go extract, not just extract what that is in nice format, read the words. We do actually have to figure out which is the right one. That's our task. And that's why this is more into the machine learning realm at that point. So now you're talking about a classification model trained on data. And that's exactly what we're doing here. So there's other people doing that too, even specifically. But we have yet to see something that would do what we want to do right out of the box, or we would use it actually. So technologies we anticipate being in our stack that we're experimenting with now, certainly in many different ways and in series and loops. OCR, natural language processing, image recognition, and of several different types too. So with that, I think it jumps over to Brandon.
All right, so I'm going to talk a little bit about how we've been applying, or the experience we've been doing with deep learning models and doing computer vision on the documents. The reasons, as Mark kind of alluded to, we need to do that is because although a lot of these documents have embedded text in them, a lot of the text in them is not that good. So sometimes it'd just be a bunch of gibberish, and sometimes it'd be slight misspellings, but we need things to be exact. So we can match the exact words in the document to the accounting documents that we need to match it to. And then another reason is that the embedded text is usually just one giant long string of text, so you kind of lose all the structure. So kind of like Mark said, you might have a bunch of different invoice dates in a document, but we need it to be if the invoice date's usually probably going to be somewhere at the top of the document, maybe on the right side or right in the middle or something like that. So what we do is we're starting to use object detection models to identify bounding boxes of where the targets are in the document. So far, we've experimented with 3 different frameworks. We've done Faster-RCNN and RetinaNet, which have both shown some promise so far. We've also tried YOLO v3, which hasn't been that great yet, but we'll keep trying. I'll talk briefly about Faster-RCNN and RetinaNet, since those 2 have worked kind of the best so far, and they have slightly different takes on how to find objects. So Faster-RCNN is a 2-stage model, which so basically it takes an image, we apply a convolutional network to it, which outputs a feature map. And from that feature map, we apply a region proposal network, which basically finds in an image all of the possible boxes that the foreground might be in. In our case, the foreground is going to be text, so it'll generate probably 1,000 or 2,000 different possibilities of where a bounding box might be around specific text. So once you have all these thousands of possibilities, a second stage applies a classification network to it. And that classification network will identify something and say, this is an invoice date with a 90% chance, or this is a stock code with a 4% chance, or something like that. And then once we have all of those, we can pretty much say everything above 80%, we're going to keep that. And anything lower than that, we're going to throw it away, because it's not useful or it's probably wrong. Then the second one that has shown promise is RetinaNet. This doesn't have 2 stages like Faster-RCNN does. This is a 1-stage detector. But the thing that makes this one unique is that they introduced a new loss function that hasn't really been used before, and that helps the 1-stage detectors. One benefit of the 1-stage detectors is that they're a lot faster than 2 stages. So this loss function, what this loss function does actually is it punishes basically all the easy examples a lot harder than it does the harder examples. So something that's hard, it's going to forces the model to focus on all the hard examples. So maybe if it's struggling with finding an invoice state, it's going to force the model to start focusing on finding that a lot more. So this is an example of RetinaNet results that we have so far. I think we started using RetinaNet about 3 weeks ago, so this is very early stages. As you can see in the upper left there, we found the invoice number. Oh, sorry, all the green boxes are the actuals, and all the other colors are guesses for different things. You can see in the upper left that it got the invoice number pretty much exactly correct. But right down there, right next to it, it totally missed the invoice date, and it totally missed the company name. Didn't guess anything there. And then we can see down in the bottom, there was a few false positives, and one where it just has a box of emptiness, which is kind of surprising, but that should be pretty easy to fix. But yeah, so I should also say that these models were trained on using, I don't know, 14 or 15 different invoice formats, which in terms of invoices is like nothing. There's thousands and thousands of different formats. So considering we use so few so far, I think this shows pretty good promise. And I think Mark's going to talk about the training set.
Yeah, so what he mentioned is one of the things we've learned. So for us, looking at this from the outset, training data is going to be critical because for these models, we don't readily have answers. You can think the natural process of figuring this out would say, well, let's get a hold of some documents and the way they were accounted for. You know, that's the natural way to grab data without trying to go do it specifically for your process. But a couple problems with that. One is security of the client's data. That's actually kind of hard to find that pool. We're not the only ones in that boat. If you look, there's some other people solving this problem, and they've reported similar examples. Like confidentiality, security, it's important. So you can't just go rating documents all the time. But the real problem is that doesn't actually help us for deep learning. What that would do, let's say we had that. So we have an invoice date here. Again, like I mentioned, there might be 100 invoice dates, and 50 of them might all be the right one. For us, we kind of want to learn the why. That's what deep learning is. We really wanted to teach it the why this is the right one, not what the answer is. Like the actual date, January 3rd, doesn't matter at all. We wanted to learn the flexibility of the thing that follows invoice date in many different languages, many different representations. Sometimes it doesn't say that at all. That's the thing that we wanted to learn. And so we've gone after these bounding box models, and so you can look in the bottom right. This is a spreadsheet view of it, but this is the data we've had to collect, which is bounding boxes. And for those that are familiar with this world, annotations. It goes by a lot of different names of obtaining these labels. This is how you do cat, dog, mouse problem. The world isn't labeled often with images, so we're not the only ones trying to do this. There are services out there that will do that for you, but then again, security comes into place and some other kind of questions. So we've gone at ourselves going simple, and what the original plan was to create templates, and so we would take care to get a few documents really correct, and you can still get through these almost as quick as you can online sort of thing where you go with high speed. But if we capture it in a certain way, we could actually get real examples of that recorded data, get that structured data, and load a lot of different examples so that it's not learning that the item of interest is a chair. Anything can pop in that chair blank, or the dates. We can rotate dates, change the formats, move them around a little bit. But that's been the struggle, is that we can't easily move around a formatted PDF, or we haven't yet. We're experimenting with that. So far, we have not done a great job. So what they left us with is putting a lot of energy into getting a few templates that we could get 1,000 of these out, but 1,000 different versions of one document, even if we switch up the characters and all that kind of stuff, we're overfit massively to the structure of these. It learns that structure, and if you put a new structure in, it stopped too early. It can't generalize to solve the new template. And so that's kind of where we're at. The more templates we add, the better off it is, but the batch size is down to 100, but really it could be as low as 1. So that's been one of the big lessons for me. I still feel I like the power of having these templates where I can doctor them and work with them in a way that's not typical with images. The PDFs are structured a lot more than regular images. I want to use that control and try to essentially randomize these, perturb these just enough so that the deep learning doesn't overfit, but that just enough we haven't gotten there yet. So a simpler method is kind of what I alluded to earlier. online annotation is a simpler way. You know, there's people that have this as a solved problem, and their tools are just a little faster than ours. But when you're doing a lot of these, a little faster is helpful. And so we've thrown 1,000 of these invoices into a tool where we're just kind of drawing boxes over things, which is an interesting process too. You know, as I kind of said a few times, we want different label types. We have different models doing different things. And so the one here, I've got giant boxes of tables highlighted in the blue, because one of the styles of models, we want to look at this. We don't want to worry about every single line item. We want to have a model that is really doing kind of a simple first pass. And so things you can do at a header level if you look at header in detail. So whether we had 1 line, 100 lines, 1 page, 10 pages, show us where the table of the data is. That's just one model we want to use in our arsenal. And so that's a different labeling state. Now, if we wanted to use this same thing to get something else, we're going to have to click again and draw these boxes. So it's been interesting. Labor intensive is definitely something I think we knew we'd be up against because we had to go from 0 to something. And so now, are there Mechanical Turk and other sort of ways of doing this? Yes, there are. And we certainly want, our process is not automated well enough. I think we would make good use of that, but we would look further because deep learning, you need more and more data, the better this will be, and it needs to be of more variety. We're missing in variety, and we need to get there, but that's where we're at. Again, we're 3 months in, but we're paying a lot of attention to this. So our fourth member, Shanshan Wang, is a data scientist aimed at this task. She is our training data owner, really, and so she's experimenting with lots of ways of adjusting the PDFs to get us so that we can get these deep learning models to work really well when we need them most, which is when we kind of have crummy scans and all of our other methods have sort of aren't returning very good information. The last bit is kind of how this plugs into driverless AI, and we can do two of these. So the part we're currently using driverless AI, I think, is a good story because it shows the power of driverless AI. Early on, when we were creating some of these templated data sets, we have lots of the data that would fool an NLP algorithm, not so much that would fool the image recognition. The ones that need structure, we have a hard time manipulating structure, but the content we can manipulate a lot. So those are more successful, and those are the ones we're paying attention to in a different kind of track, if you will. So Brandon and Shaiket tend to be doing the deep learning models. I've been doing some of these other ones. And so one of the first ones to come alive was, first we started with almost first principles. Like, let's just pick the first date you see, just as a benchmark. How well does that do? Not very well, but at least we have something. So the next one was to use driverless. And so realizing that a really simple way of what I'm looking for is to, when we do have that embedded text, or we can use OCR to obtain it, which is the majority of the documents, the large majority, in fact, of the documents, you can obtain reasonably good text with that. And that's kind of on the right. If we look at every single line just in simple form, we can use our existing labels to figure out whether these targets were in there. Once we have the bounding boxes, we had another way of going after them in simple terms. And so the rightmost column is actually going to say the target class. And this is just a standard machine learning problem at that point. So with text, with NLP. But we have that in driverless. So once I created this data set, fed it into driverless, and again, we're still struggling with the variance even for the NLP. We've gotten a lot better since I've tried this model, but it was at 100%, 99.9 AUC, almost immediately, like within 5 minutes of running a driverless model. The work was to get the data to go into it. The model itself was really simplistic because it's actually pretty easy to figure out all the terms we fooled it with. We have a kind of a list of terms that we put in there to jostle a little bit, and it figured those out pretty quickly. Enough of it, some of the structure, a little bit of the structure. It hasn't figured out too much vertical position on this one, but it does a really good job of figuring out what we were looking for. So the way of using driverless was actually pretty easy. It's more of thinking of how you get the data into driverless, and I think that's kind of a data munging problem. So here, we're so familiar with our training process, I think we will see this time and time again. Like, there are, just in the way that we're going to have multiple different image models going after different variations of the targets, I anticipate we will have multiple different driverless models out there all doing different things. So right now, the driverless model will only take you halfway, just like an image model will. If it shows you the bounding box, that's great, we still need a formatted answer in structured data. That's not the hard part necessarily, the hardest part. But we need it from here too, because I've labeled the entire string. You know, it's a pretty stupid parser, simplistic I should say, parser. Every new line is it, and we just encoded as a target whether the presence of that string was there or not. So we then have to extract the data out of this one too, but that's fairly simple actually with what we're looking for with 2 of these 3 targets, trivial in fact. So this was nice to see. I didn't have to think much. You know, that's the idea of driverless. You know, I spent all my time thinking of everything else of this problem. The model itself, I didn't have to code at all. I didn't have to do any of the typical NLP transforms. You know, those are done. Some of them are done. We're making that better, but you know, we have all the way our target encoding, and our text CNN was used for this one to do the job. So that was pretty good. The real goal of this project, and this is kind of exciting, you know, a lot of the work we've done previously, we haven't been able to include back into the tool other than, you know, reports. So, like, it's helpful to have us with the customers. You know, before I was working directly with a customer, you know, it was, you find something new every time you deal with a customer data set, it feels like, and that's true before I worked at H2O, everything. You know, it's just Kaggle, I was amazed at the diminishing returns, you know, just the law is just a little, the slope is a little different than normal. Like, it feels like you can keep doing competition after competition, and just every data set is going to bring out something different, it feels like. And so here we have the opportunity to push this back into driverless AI, and that's connecting to you. At some point, our goal is so that you can pull down the results of our work. You know, sometimes that's maybe too narrow-minded for a lot of people. And so, you know, a specific version would be this invoice to vec, something like that. Like, we'll load a document. Maybe it's not an invoice, maybe it's something else. We have the terms we've looked at, very much like a deep learning pre-trained model in that world, and a vector of what we think the probability is of the known classes that we've gone after in the past are trained on ours. That's a possibility. More generally, you know, also either in addition or if that proves too hard, but I don't think it will. That's really our goal, is to get that in there in some way, shape, or form, because we're going to use it ourselves. You know, that's the best way of building these products. We used to build H2O3 that way. You know, when customer didn't have what they need, let's work on that. So, and that's the way we're kind of trying to do this one. But in general, there's a couple other ways we can do that as well. Just taking the tips and tricks, like that's how Driverless was built. It's taking grandmasters who've done, you know, hundreds and hundreds of data sets. And, you know, the learnings of that is how Driverless came up from specifically Dimitri, but as it's been added onto. So that's sort of what we could do too. As we're experimenting with the image domain that we're not paying too much attention to otherwise at H2O, you know, maybe we're allowed to you know, or we're able to advise on how that comes into the tool, or maybe we just extend the NLP models, because we have that kind of need too. We're already using the NLP models. We can already see we need variants of that. So we'll probably see maybe all 3 of these classes improve. So, and that's it. We're out of time. Thanks for listening, and hopefully you'll see the results of our work soon.